everyone. I'm glad to be presenting here. Today I'll be talking about having a small seminar about reversing and more specifically about reversing modern binaries. We'll try to talk about common challenges and have some approaches which could help you with reversing modern binaries, I guess. So a bit about me. What's relevant for this talk is that I work in security. I also play CTFs. I've been playing CTFs for around 2 years. I play for WaterPaddler and Blue Water. At work, I'm doing for CTFs. I'm doing pawnables and reversible challenges mainly. So I mainly focus on binary exploitation or binary reversing, and I do a bit of crypto as well. And at work, I'm doing blockchain research, looking for bugs that could cause loss of funds on some blockchains. I also teach at Free University of Tbilisi, and I'm also a retired competitive programmer. I used to do ICPC and IOI before. Yeah, here's my Twitter ID if you want to follow, and if you have any follow-up questions after the talk, feel free to message me. Yeah. So a quick reminder on what is reverse engineering. Reverse engineering is a process of recovering information from which has been lost during the compilation of some specific program or project. This information could be function names, which were in the original source code, the types or structures or field names as well are all information which a developer wrote into the source code, right? Also variable names, comments, all of this information get lost during the compilation steps, and everything gets transformed to assembly, which kind of resembles what the developer wrote, but it is not the perfect information. It has lost information, and the task of reverse engineering is to recover this information from the binary and understand the intentions and logic that the developer wanted to write. CTF challenges and small binaries all have low complexity and mainly have no dependencies, are written in C, and sometimes they are not well representing of realistic programs which you might find in today's world. And on this talk, I want to talk about real-world programs, and I want to realize that the reality is that complexity of modern software is ever growing. For example, this is a graph of lines of code in Linux kernel, and I think it's above 20 million lines now. And a lot of the code is also back from 2000s or so. And this complexity is not just in Linux kernel. If you see any program that you use today, like browsers, messengers, any closed source programs are growing in complexity, and reversing them is getting harder and harder. And so that's why let's talk about common challenges that you might meet in reversing real-world modern programs. One of the problems is that they're, of course, as we said, is high in complexity. They are large in size. Just the sheer amount of code that you have to reverse is it's a lot. And also, the abstractions are getting bigger and bigger. There's many dependencies that these programs use. The new programming languages are also getting popular. With those, we also get a lot of static compilation because those are more useful for deployment and containerization. There's also more optimizations coming in, and all the developers are also stripping their release binaries or the production binaries. So reversing is fighting against all of these challenges, and the list never stops because the challenges are keep growing. Yeah. So I want to talk about how not to get overwhelmed when you get started on reversing a huge binary. The first, and I think one of the most important one, is to have strong fundamentals. In general, when I teach security in my school, I have a lot of prerequisites, which I say that you must have good computer science knowledge in order to get into security, because if you understand what goes on behind the compiler, if you understand how assembly works, how allocators work, the reversing is much easier because you can like look back to that knowledge and use that for your intuition during reversing. So that one is one of the first steps. And specifically when reversing large projects, I think you have to focus on what matters, because ultimately you won't be able to reverse the whole Linux kernel, or like Linux kernel is open source, so you don't have to reverse. But if you imagine some closed source program like maybe Discord and you want to reverse it, then it would be impossible to go through every function, because it is a result of work of many developers over years. It's impossible for a single person to understand every single function in a huge binary. So you have to focus on what is your objective. You have to focus on what you care about, and try to find tricks and like try to approach the binary in a way where you will only focus on what matters for you. Like look through the strings, find the references to the functions where the strings are used, and try to find the relevant functions that you want to reverse only, and don't focus on what does not matter to you. And another one that I want to focus is using tools, because once you have a binary which is huge and impossible to reverse entirely, sometimes the tools or automation is key to solving them, because if you have an objective in mind and you can somehow automatically look for it, or you can somehow automatically reverse a part of a function for every function with an automatic tool, then those are really useful. And that's what I want to talk about today as well. So one of the common challenges that today's modern binaries face when reversing is that though many of them are using imported libraries. So if you imagine some program that needs to do some cryptography, of course, the recommendation is to not roll your own crypto. You have to use a library like OpenSSL to implement secure cryptography. And this does not only work for cryptography, but also mathematics, graphical user interfaces, and other OS features as well. And the interesting fact is that many of these libraries, which closed source programs could be using, are actually open source. And this could be something that we could use to our advantage as reverse engineers, because even if the whole like complex binary is closed source, the library that they use might be open source, which gives us information about their own code as well. So this might not be a challenge, but a good part where like we could use this to our advantage. For example, one automatic fact is that shared library functions, when they are imported, have to be imported with their real names. So their original symbol names are already exposed in the function. So if you look into a binary which uses some shared library, you will be able to see that the function call names will not be removed, will not be stripped, because in order for the binary to call a shared library, the function name has to remain in the binary. We will see this in a bit in the example that we'll do. But the question is, can we go even further? Can we not only have just function names be automatically reversed in such binaries, but use the fact that these libraries are open source, and we could look into their source. We could extract some debug information from the source code of these libraries, and somehow use it to our advantage to automatically reverse the other parts of the lost information that we were talking before. So this could include types, variable names, field names, and other such information that could be useful for reversing process. So to show this, to show how we could do this, I want to do a quick working challenge, which is from 2022 version of D3CTF. This CTF is not very famous, and this challenge was also not a hard challenge, but it is a good example where importing libraries is useful. So let's talk about this challenge. The challenge was a clonable challenge, so binary exploitation challenge, where you had a implementation of a Fuse file system. For those that don't know what Fuse file system is, it is a way to implement a new type of file system like ext4 or NTFS or such in user space. So it's a Linux feature in which you can implement a new file system without writing your own driver. The way it works is that you just have a special interface which you have to implement for your file system in the user space, and your user space binary will simply implement this interface. Once you run it and attach it to a specific like mount point, then the file system operations on the specific mount point will go through the binary which implements the Fuse. Let's look at the challenge. Any questions so far? Feel free to ask them already if you have. Or we can do questions and answers at the end as well. Yeah, so this is the files from the challenge. I think it's not available anymore where you could actually solve it on the original server, but since they provided a Docker file, the challenges, you can still work on it yourself. And we can see that there's a binary, D3 Fuse, which is a normal Linux binary. We can see that in the README, how to run the challenge. And there's a Docker file. We can look into the Docker file, which simply copies the challenge and starts script into the Docker container and also creates a flag at the root flag directory. And the Docker file starts the shell script, which we can look into. And the shell script runs the challenge binary in background, and we can see that it then gives us shell. So if we run this challenge, and I've already run it in Docker because it takes some time to get started. So I already have it running on localhost 999, and if I connect to it, I can see that I have access to the shell inside the challenge, and there's a mount directory which is a bit weird, and I guess we have to find out what the D3CTF binary does, because for now I don't see a flag file, and I don't see the mount anything in the mount directory as well. Yeah. So let's open up the binary in Ghidra, which will be the tool that I use today. But you could work on this challenge in IDA as well. But the tool that we will be seeing about for importing library types is in Ghidra. So unfortunately, you will have to use Ghidra for that. So let's first just try to reverse this binary ourselves without any new tools. And let's open up the binary. Yeah, let's analyze. I think this binary itself is not super big, but it's good for demonstration purposes. So we see that all the symbols are strict. So let's try to find where the main function is. We know that the main function will be in entry, the first argument to libc start main. So we can rename this to main, and let's look at what main does. And we see that main is not doing much. In fact, it's only calling this Fuse main real function. So I guess it is a Fuse implementation, and then it's calling this function, which is just a free function. So this doesn't do much. So let's look at the documentation for Fuse, what this function does, because here it's not easy to reverse for now. Unless we know what Fuse file system is or how it works, but you don't have to know that for now. Yeah. So Fuse main real is the main function for Fuse. Like it says that this is for lazy, and I won't be reading the whole documentation. I'll just say that this will provide the implementation of the file system from the user space to the operating system. So if we look at the function, we can see that the main argument here is this. Okay, we see that the main argument here is this fuse operations function pointer. And if we look at the structure, we can see that it has it's basically a structure with a lot of function pointers. So you might be able to recognize some of these functions like open, read, write, get, attr. These functions are all functions that Linux file systems in general have to implement. This data type has to be implemented by the user space binary, which wants to provide a fuse file system. So if you want to create a new file system, you have to implement these functions. You don't have to implement all of them, but you have to implement like open, read, write, and such. And then the file system operations will be forwarded to the program like this one. So we can see that this third argument is supposed to be this structure. So let's look at it. This is a static definition of the structure, and we can see that there are a bunch of function pointers, and some of them are implemented and some of them are not. So if we see this first function pointer, it's supposed to be this get attr function, and if we look into it, the signature of it looks the same as well. Like it's probably only using 2 arguments, and the third one doesn't matter. So I guess this is the get attr function, and yeah, in the structure we can see other function implementations as well. So what this means is that we can look here in the main function again, or in the start script, sorry, we can see that this diffrefuse binary is mounting itself into this mount directory. So the diffrefuse itself is running outside of the change root sandbox, and it is creating a fake file system, which every operation on this file system, like open, read, write, will be forwarded back to this binary into one of these functions. So an open call in this mount folder will be forwarded to like the implementation of open in this binary. So this is the kind of challenge that we're facing, where the shell that it gives us allows us to access this mount directory. So by going into this mount directory and, for example, creating files, we are basically communicating with this binary. So doing any file system operations will talk with this binary. Yeah. So I don't want to fully focus on solving this challenge. Now I want to show you a trick where we can automatically import like all these structures that we see here into Ghidra to help us reverse this binary. So for example, now if we look at again like main function, we can see the fuse main real function, this structure, and it could be useful to automatically see like which function is this, like which of these functions is this, or which one is this. Like having the structure definitions inside Ghidra would allow us to directly see all of this. And additionally, if we go into one of those, we could automatically also see what is the signature of this function, because all the signatures here are known. So importing these types into your reversing process could really speed up the reversing process of this specific binary, or binary which depends on any shared library. So let's try to do that, I guess. In order to get started on that, we first have to figure out what is the shared library that it is using. So here we can use LDD command, which will tell us all the libraries that the specific binary is using. And the one that we care about, or the one where we want the types from, is libfuse3. So we want to get the type information from this library into Ghidra. One way that you might have heard of it, and you might have tried, is to use Ghidra's function, which supports, I'm not sure where exactly, Ghidra has support for parsing like C source code. So we could download the source code of this library and allow Ghidra to parse it. But in my experience, this feature is very unreliable. It doesn't support many of the C features, and most of the code bases are basically impossible to like parse through this functionality. So unfortunately, I think this way will not work if you were to try this. So I want to try another approach, which has been very reliable for me, and it is to compile the library, in this case libfuse, with debug symbols, and import the debug symbols with type information into Ghidra. So to do that, we have to first look up the source code of libfuse, because we need to recompile this binary. So we could look up libfuse. It's this one. To be more careful, it would be good to check which exact version the binary is using and download the specific version. But here, since the structures and functions are stable, I know that they're stable, so they have not been modified during the versions. It's okay to download the latest one. But if you were to solve other challenge, or if you were to do the same thing for other library, you might need to make sure that the version is correct. But here we can just clone the latest version of libfuse in order to compile it. And for doing this, you don't have to know exactly what the library does. So now we need to figure out how to compile it, which is very common to be written in the README, right? So if you want to compile this libfuse, we can see that you have to create a build folder, go into build folder, cd build, and then do like this one uses Mason for setup, I guess. And I guess let's first try to compile it normally without debug symbols. So here it says that this is for configuring it, like if you want to change any configuration options. We don't want to change it for now. So to build, we just need to run Ninja. This will compile and give us the library in lib folder. So we have successfully compiled libfuse. But if we look at libfuse, there is some debug info, but we want to compile this library with a specific debug symbols, which is called dwarf. You might have heard of it. Dwarf is a debug information type in ELF files, which gives debuggers and reversing tools access to information like structure fields, structure sizes, and such. So for GCC, in order to turn on like the compilation with dwarf symbols, there is a flag called gdwarf. Like if you pass in this compilation flag to GCC, it will attach this extra debug information to the binary that it generates. And specifically, Ghidra only supports version 4, so we want gdwarf version 4. So I will configure now this build process with this flag. So we can try Mason configure to see like how the configuration for this specific library looks. And here is every like configuration flag that this process supports. And we want to add a flag to GCC, right? So we are looking to this option, which is a cargs, which will, whatever options we set here will be passed into GCC. So we just want to change this one to include the gdwarf argument. So I already did this, so I know the exact way to do this. So it's a Mason configure select -t, and you set the cargs like this. So we are setting the gdwarf for, and also on GCC, if you specify the optimization level of G, it will add even more debug information, which is sometimes useful. I'm not sure if this is needed, but I think it doesn't hurt to have all debug information that's possible compiled in. So we can even look at the library, like how big it is before without debug information. And now let's configure it with the debug information and recompile it with Ninja. And now we can see that before it was 700 kilobytes and now it is 900 kilobytes. All of this new like 200 kilobytes is the debug information which has been like compiled into the binary in order to help you reverse or debug it. But we want to use this information for reverse engineering other program like the challenge that we have. So now our goal is to somehow get this debug information into Ghidra. And for that, I have there's a good blog post which I'll link in the presentation afterwards. But there's an extension for Ghidra which I have written here. Sorry. Ghidra supports like converting this dwarf symbol information from dwarf symbol format, which is like from the binary, into like a file called GDT, which is a Ghidra definition file, which Ghidra itself knows how to understand. So right now we're trying to get this like type and symbol information from this library into a format which Ghidra could understand. And for that, we will use this small Ghidra script, which will basically check if the current program which is open in the Ghidra has any dwarf symbols, and then create this GDT file, which is a format that Ghidra understands, and basically dump all of the debug information from the current program into this GDT file. So the specifics of this is not super important. And the script is very simple, and basically most of the hard work is done on the Ghidra side, which knows how to parse dwarf symbols and convert it into its own format that it will understand or be able to import into other projects. So for that, I'm going to use Ghidra's version, which will simply run the script and in terminal. So it's a bit of a long command, but it doesn't matter. The details doesn't matter. So we are doing Ghidra's analyze pass on this libfuse binary. So this is the binary where we want to extract the types from, and where the rest of the arguments is basically just saying to run this script on this binary, the script that we wrote or we saw before. So hopefully this works, because sometimes it had problems. I'm sorry, yeah, I'm in the wrong directory. Yeah, let's run the script again. This is basically running the script on this binary, and it will convert the dwarf symbols into GDT and give us the file in the same directory. Yeah, so we can see that we ran the script on this, and we generated this GDT file. This file is not something that is a famous file format or something. Even file command doesn't fully understand it. It is basically a serialized version of the types from dwarf symbols, which we can now import into Ghidra. So let's see how we can do that. Yeah. So we can use this open file archive, and we are basically in the correct folder where we see the GDT file that we generated. The GDT file can be imported like this, and now I see that Ghidra can now see all of the types that are used, or these are the functions that are in the library, or all of the types as well, which are defined in this library. So, for example, the types that we were looking at before, what the type was this one, like the fuse operation structure, right? We had it was used from the main function. Yeah, let's look at it once more. We can see that the main real function gets its third argument as this structure's pointer. And let's see if we have the structure in the generated symbols, or I guess types. And we can see that now Ghidra has this structure type, and if we open it up, we can see that it is equivalent to the one that we see in documentation. So we have successfully imported this structure into Ghidra in a way where all of the arguments and structure types are all well defined and will automatically help us reverse this binary. So now we can basically use all the structures however we like. So in the main function, we knew that like this area of memory was this fuse operations type. So we can just set the type on this, choose data type, and we know that this is the fuse operations structure. So we just set it, and we can now expand it and see exactly which functions are not defined, which functions are defined. And we can see, for example, that this one is open, this one is read, this one is write, or truncate. So we have automatically, like, without manually going back and forth within the structure, reversed all of this. But this might not be super useful. So we can even go into one of the functions and see if we can reverse the function implementations as well. So now that we know that this is read, we know that read's signature looks something like this, right? So we can rename this function to be read. Let's first rename. Yeah, I guess rename. Fuse read. We can call this fuse read. And now the signature is not yet automatically updated because Ghidra is not smart enough to connect the dots and to automatically like change the types of this. But since we have the structures defined already, it is quite trivial to like copy over this signature. So we want to see what type is the read in Ghidra itself, and we can see that read function is this like weird long type, but it doesn't matter exactly what this is. We can just copy it and find the definition of it. So this is like this long line. Let's just copy it and look at it in editor. Yeah, this is the definition of this function in Ghidra. So we can just copy this this format and set this signature to our function. So we just call it a normal name as well. And we can see that all of the argument types have now been fixed. And for example, the one that is the most interesting is this param5, which is this fuse file infrastructure. So let's call it file info. And we can see that its field has now automatically been reversed. Unfortunately, Ghidra, again, is not smart enough to automatically like guess what type the UVAR1 is going to be now, because we see that it probably looks like a structure, because look, there are a lot of field accesses here, and technically it knows the type of this FH from the structure. So we can see that this FH, FH is just an unit. Oh, I'm sorry. Yeah, I think yeah, this one is correctly reversing. Then this is not the correct type. So since the binary or since the source code itself does not define what exactly the file handle itself points at, it now doesn't know the structure of this right now. This is not something that we could get from the library or the generated types, because this is user defined. This has to be actually reversed because this does not come from the source code. I think this is user-defined structure, so that's why it's not able to reverse this automatically. But we can take a look at any other structure which could be useful, and like try to see if that one can be reversed as well. So if we go into this like long list of functions as well, we can see like For example, this readDir function, we can see that it uses, again, a lot of structures, right? So we can try to look into that one as well, just to demonstrate that the signatures can be, how helpful the signatures can be, I guess. Yeah, let's check out the fuse operations once more. We want the readDir. Let's quickly find the readDir. And I just want to copy out the, I could copy the signature from here, but this will not be able to be automatically imported into Ghidra because it's written in a different syntax. But this one, the Ghidra syntax, works directly. So here I can just import this types, and this function we know is called the fuse readDir. And we can see now that the whole code has been is better reversed. We again see this file handle, which is user defined, so it's not easy to be reversed. But the rest of the signatures, like param3, or we know that this is the function pointer, so it's well reversed. And we see that all of the types are now important and automatically reversed. So this this trick of importing types from libraries or open source libraries can be applied to not just this challenge, but any binary which uses any open source libraries. This could be even used for libc. This could be used for like OpenSSL or any library which you have access to to source code, and you can recompile it with dwarf symbols. You can then again, just to repeat, we can extract the symbols into the GDT file and just import it into Ghidra. Another common use case for this, for me, is if you have, for example, a Linux kernel, which in general is open source. But for example, there's a challenge or a closed source embedded device which implements a custom driver or a custom version of Linux. 90% or 95% of the reversing for this specific Linux kernel will be the normal open source part of Linux. So in that case as well, we can compile the version that we have access to, the normal Linux kernel with these dwarf symbols, import it, and use the structures and function signatures that we import into the reversing process of a modified Linux kernel or a challenge Linux kernel. So in any challenge where a part of reversing process is reversing of open source code, this approach could be helpful. And yeah, I will post links to all the scripts and commands that I used for this. And I will also share the challenge as well, which you could try to solve it without this, or even try to solve with this trick. It is a clonable challenge, not just a reversing challenge, but it's not super hard. So I recommend you trying it. That's the first part of reversing the modern binaries that I wanted to focus on. I'll take questions about this at the end, and now I guess I'll continue a bit talking about other challenges, which specifically now I'm going to talk about binaries written in modern languages. So in the last decade, we know that many companies or many developers started caring about both performance and security. Like before this, the only solution when you wanted performance in a program was to write it in C or C++. But unfortunately, we all know that software written in C or C++ leads to many vulnerabilities which are exploitable, and it has been well documented that this is the case. So in the last decade, many new programming languages have risen to have grown in size, which include Rust, Go, or even Zig, and these all provide memory safety with performance. But since this is a reversing talk, we have to consider that now that these languages are getting more popular, some of the closed source applications, which we might need reversing of, might be written in one of these languages, which means that all of their weird features or all of their weird compilation tricks, which are different from C, will get in the way of reversing binaries written in these languages. So one thing that I want to say is that don't just assume that if you're good at reversing C, you'll be immediately good at reversing Rust or Go. There is a learning process to learning to reverse a new language, just like there is a learning process for just using the language. So I want to talk about some common challenges and how to solve or get around the challenges when reversing binaries written in such languages. So the first one, that is the one that most people meet, which is not super complicated, is that these new languages all generally don't avoid to use null terminated strings. So we know that in C, when you define a string, the length information is not attached to it as an integer. Length information comes from, you have to get the length by calling strlen function, which will just iterate over it and find the null terminator. The fact that strings are written like this in C is good for reversing, because when you open up a binary in Ghidra or IDA, they can automatically see where the strings end by just seeing where the null terminator is. But in the case of Rust, the strings are stored like this, where you have a pointer and a length. This means that you no longer have to store an extra 0 at the end, and this means that all of the strings that are statically defined in binary can all be concatenated together without any zeros inside. So this makes the reversing programs like IDA or Ghidra confused. And we can see an example of this as well from a small binary from a recent CTF challenge on DEF CON, which was called Safer Rust. And you can open up this in Ghidra and just see how this fact that Ghidra or Rust stores strings without any null terminators affects the reversing decompilation results. This challenge is also opponable from the recent 2024 DEF CON qualifiers. In here, you had to do quite a lot of reversing if you approached this challenge with the reversing way. There was a way to just never reverse and only use dynamic analysis for this challenge. But when I was working on this challenge, I tried to reverse it, so I had to fight the common Rust problems. And we can start, you can see how that looks. So in Rust, so in order to find the main function, you have to first go to the normal main function, and and then there is another, this is the main function of the Rust runtime, and the actual function where the most of the logic is, or the user code is in the Rust main, which might not be called like this because this is strict library, but this is where the most of the logic or the code for this binary starts. And you can see that Ghidra is pretty good at reversing the strings already. Before, a few years ago, if you tried to open up a Rust file into reverse engineering tool like Ghidra, the strings would be very confused, because if we open this up, we can see that all of the strings here are concatenated together. We can see that when this single string, say file2 ends, there's no 0 between these. And in general, these ones are okay, but we can see that some of them are still problematic. For example, mainly look at this one. Here we have some error messages, which looks like a failed to read line. But since Ghidra is not able to figure out where this string ends, if we open it up and see the definition of it, we can see that this is just a bunch of strings which are all thought to be a single string, but in reality it's not a single string. It's supposed to be just this failed to read line, and this kind of makes reversing process a bit tedious, but fortunately there are extensions like this, Rust string slicer for binary ninja, which attempts to find the length information encoded in the binary like this, since the strings have to have a length attached to it somewhere. Many times it is able to guess or find about the actual length of the string and correct the length here. So for example, if we use binary ninja and use this extension, it would correct the strings and guess where they start and where they end, instead of showing them all concatenated together like this. So this is one problem that you might face in Rust, and it's not also only to Rust. Go also uses the same format for strings, so you might see the same problem there as well. We can also, just by looking at this Rust binary, see that there is a lot of boilerplate. So we can see that even for a small returning an error, there's many arguments. There's all the code around this is all just printing an error. So Rust binaries tend to be much more verbose, have a lot of boilerplate, which makes reversing a bit hard. Another caveat that you have to know about specifically about Rust is that compared to C, it has support for sum types or enums. This is a type where which can be either one or two of the variants. So for example, if you want to support a user ID, which can either be a number or be a string. So for example, like car pointer. In C, you might have to use you might have to have a structure which will store both of these versions together. So and only use one of the fields. Or if you are if you know more advanced features of C, you could also use unions. But those are much harder to use compared to Rust enums, where you just have a type which can either be a number or a text. And the memory storage of it looks like this, where Rust automatically creates a new field, like a hidden field, which will be stored at the start of the structure called discriminant, which will be 8 bytes. So with this field is telling you which of these variants is currently stored in the structure. So if the user ID was a number, then discriminant will be 0, and if user ID was a text variant, then discriminant would be 1. And depending on the discriminant, the rest of the bytes, the 8 bytes, have to be either interpreted as a number or have to be interpreted as text. So this is, of course, a really good feature for Rust, which lots of developers love. But when you're reversing Rust binaries, this is pretty hard to handle, because most of the tools like Ghidra are written for C, and since C doesn't have this feature, they are not really suited for reversing these types, because when you try to define a new type, there's no way to define this enum variant. There you have to do unions, which are also not very comfortable to use. When I was reversing this binary, and one of the challenges was handling these enum types. So my advice for how to handle this is, in general, like when you're reversing Rust binaries, you have to understand well what goes on, how the memory layout of enums look. You have to know that these types exist, and unlike C, that you have to expect that the same area of memory could be used as a number or as a text. So you have to be aware of this feature, and in general, consider it when reversing Rust binaries. Other challenges that these new languages impose are dynamic dispatch, which is where you are using interfaces or like object-oriented programming tools like interfaces or like inheritance, and you are, instead of passing in a specific type, you're passing in an interface which could be implemented by many types. Well, the dynamic dispatch problem is well known from C++ as well, so the reversing tools are kind of used to it, and vtables, you just have to know how vtables work, and in general, understand how the dynamics dispatch works in the background, and reversing it won't be too much of a problem. Another problem which is common is deep abstractions. So, for example, if I press on a random function in Rust function, I didn't like even know exactly this function, but I can see that it goes in depth like 10 levels. So this is very hard when you're reversing. And my advice here is you just have to like focus on what you're interested in. So in this challenge, I would like use these strings as a guide to understand where exactly in the logic the binary is, and like ignore any functions that I'm not interested in. So like if I want to, since I want to look at the main logic where I enter my name and then the challenge goes on, I will only look at the functions past that point, or use these strings or error messages and any like side information that I can leverage to guide my reversing, and use it to focus on only what matters, because otherwise these huge deep abstraction layers will get you lost. One more trick that I wanted to show today as well is a way to get structure layouts of Rust types. So we can create a new small Rust code. New. So, for example, if you're interested in how a hash map, or like, for example, let's, for example, first look at a vector. So imagine you have a vector of UX, and you create it, and imagine that you have to reverse a code which uses vectors, and you want to know what the layout looks like. The first advice, of course, is to use like editor tools like Rust Analyzer to explore these types. So if I press go to definition in my editor or in VS Code, I would see that the vector looks like this, where it creates a it has a buffer and a length inside, and then this row vec itself inside contains this pointer and capacity. But generally, this sometimes gets very complex, where you have to go through a lot of code to understand how a structure looks, what a structure exactly looks like, what fields it has, what is its size. And one trick that I found in Rust is that you can use a feature called feature for when building, which will print out any type sizes that you use in your code. So here I'll look up the command itself. Sorry. Wait just a second. So we want to use this feature called print type sizes, which is a Rust flag that you can pass to any build process. So let's just copy this one and copy it and use it for the binary that we wrote. So for the program that we wrote, so we are using evacuate. So since Rust will be compiling this type during its compilation, it has this feature where you can ask it to print out like any types that it generates during its compilation, print out its size. So this is the kind of verbose output that you will get in this case. And If you're interested in specifically, for example, a back size, so let's clean this output and let's just store this somewhere. So let's store it in some small txt file and open it. This is like all the structs that were generated by Rust during this compilation process. For example, we can see like this placeholder structure, which it generated was 56 bytes. This arguments was 46. And since we are specifically interested in the U8, and since this type had to be generated by Rust compiler, this print type size feature will print out any types that it will meet and its alignment and its fields. So for example, this vec, if it was not clear from the definition, we now for sure know that it will be 24 bytes long. And it has a field which is one path, which is 16 bytes, which we remember was row vec, and it has a length, which is an 8 bytes long one. And if we're interested in the row vec details as well, we can see that this capacity and pointer is 8 bytes. And the third field that we saw is actually a 0 bytes field. This is a weird Rust feature. And if you don't know that, you can just use this hint as a way to understand these fields. So you now know that this one was a 0 bytes using this feature. And sometimes this won't output nested types from the std. So you might have to pass in another flag, which is called build std. And as a result, also have to specify another argument. So if we do this as well, it will output this type information for all the types in the Rust standard library. So let me just copy paste it. 1 second. Yeah, if we copy this one here, and for example, let's use a different type now. Instead of using the vector of U8, let's use, for example, hash map of, for example, U64 to U8. This is a key map, the dictionary, which has keys as U64s and U8s as its values. And let's create this one. And let's see how big this struct would be. Like, if you know that during reversing that you are looking at hash map U64 U8, you could use this feature to automatically get the size of the structure by just running this command. So this one will take a bit because it is rebuilding the Rust std. So instead of waiting for this, we can simply, or we can just wait for this, I guess. I already ran this on another computer, but we can run this on my laptop as well. And we can see that this file is much longer. It's like 29,000 lines long. But if we're interested only in like how big the hash map is, we can see that since std is using different types of hash maps as well, it is writing the size of those as well. But we are interested in the U64 to U8 one. And we can see that the std collection hash map will be 48 bytes long. And it will have a single field called base, which is again 48 bytes long. And this base field is of this type, and you can see that the table inside will be 32 bytes and hash builder will be 60 bytes. And this information might be useful for you to create structures in Rust. So there's also one small extension that I want to call out again. Let me Google it 1 second, or I'll just link it to it, which supports taking this output and importing it into Binary Ninja automatically, just like the example that we did for the dwarf symbols. But one small negative for that is that it won't be importing nested structures. So for example, if this table is not a primitive type, it will simply create like a car 32 size field for it. So unfortunately, the this feature is not fully supported, where you could like export the types from Rust and import it into Ghidra. Only the top fields will be able to be imported, and you have to fix up the rest. But it could be a nice project for some of you maybe to do at some point, or yeah, it's a nice project which I think should be doable, because you could like tie into the Rust compiler and like generate enough information to create all of the fields and nested fields in Ghidra structures. But for now, I think this is the only information that you can get out of Rust compiler automatically. Yeah, and this doesn't work for just for STD types. If you have any library in Rust, you can just like if you have any like my type, this feature flag will print out the size of your type as well when compiling, and you could use that when you're reversing any Rust binary. Yeah. So there's also another problem called symbol mangling, but most of the decompilers have solved this by now, so you might not even notice it. But sometimes when you open a Rust binary in an old version of the compiler, it used to have like this weird encoded symbols. But today, I think even Ghidra and other languages, if the binary has a symbol, will automatically demangle the symbols. And there are many extensions for doing this as well, which you can Google. Yeah, I guess that's the main topics that I wanted to talk about today. Again, I'm linking my Twitter in case you have any questions or want to keep all of questions, and please ask any questions that you have now as well. Yeah.
There's a list in the chat if you can access it, maybe.
Okay. Yeah.
You see the link, maybe I post it again.
Yeah. Okay. Nice. A lot of questions. I like it.
Just choose any that you like.
Yes. Yeah. The first question is about automation for finding important punts in big binary. And do I suggest writing bio scripts or using anything specific that is already available? Yeah, that's a great question. I suggest both exactly. Like, for example, any scripts that we just demonstrated will help you reverse a specific binary that you are working with, a specific library that you're working with. But in general, I do find helpful writing bio scripts if I know that there is something automatic that can be done in a binary. Yeah, I hope that answers this question. Yeah, I'll look at other questions as well. Yeah, the second question is about whether something could be done on Ghidra or IDA or Binary Ninja side to help improve reversing Rust and Go. And I think there is a lot of room to improve here. Because they are not well suited for like reversing Rust. For example, the specific problem that I talked about enums is are not well supported in Ghidra or IDA, and they're not able to easily recognize them or automatically generate them. And also, even if you know the exact type that you're looking at, you understand it yourself and know the exact enum that this is, there's no easy way to communicate it to IDA or Ghidra as well, because they don't support it yet, because C doesn't have this feature. So, for example, exactly enums is one feature, or automatically understanding where options are, or other types that are seen commonly in Rust. Yeah, hope that answers that one as well. What can you do doing with? Yeah, shrink the size. So this one is asking about Rust structs, which could shrink or expand in size in Rust. I think those are not very common. So those are mainly like vectors or buffers underneath the B-tree maps or hash maps. So I think those are not super problematic when reversing. So if you know the structures, like the static size parts, then you just have a single pointer which you know is dynamic. So I'm not sure if that's a problem, and if there's a solution as well. Yeah, I'm not sure for sure. Yeah. Yeah. The third one is asking about why, I guess, talk was about C and Rust, and why about what's compared to C++, I guess. Yeah, in general, the comparisons between Rust and C++ are all around the internet. For me, I prefer Rust in general because whatever you need to write in C++, or if you require performance of C++, you can technically get that from Rust as well, and it guarantees memory safety. So, but I think there are many people trying to make C++ safe. There's a recent development as well, where people are trying to somehow make C++ maybe as safe as Rust. But since Rust guarantees it from the start, I think that's why it's a bit better for now. Job markets that require this kind of skill sets, or is this just a hobby? The only use case I can think of at this moment is jobs that involve processing transfers. Yeah, the question is about what are the jobs for reversing in industry, and yeah, I think I'm not super familiar with this field because my work involves mainly reading source code. So for me, this is just a hobby for me personally. But as the question itself says as well, the reversing field is mainly big in malicious code reversing. So if you want to understand what a specific malware or ransomware or any virus does, you have to use reversing there. And that's the main job that is public. There are also some shady companies which use reversing for malicious purposes, but of course I won't be recommending those or anything. But the skill is mainly, I think, big companies use it for reversing malware or any payloads that could be used against them or against people, to understand what they do and who wrote them, and stuff like that, I guess. Yeah. Yeah. Another question is how to get better at reversing besides understanding how compilers work, assembly works. And in general, I think the answer to that is practice as well. For me, the best practice, the best solution is practice, like solving CTF challenges. Maybe even if you have a specific program in mind that you want to understand how it works, you could try to reverse it. You could challenge yourself with like very hard reversing tasks and practice and also knowledge. Yeah, both of those really help. But I think main one is practice and strong fundamentals as well. Just reading about anything that you don't understand and trying to like work through it and understanding it fully. Yeah. Yeah, another question is asking about obfuscation methods or making the reversing process for programs harder. I have not worked on the defense side, so on the side which tries to obfuscate binaries. And in general, my opinion is that like any obfuscation method will somehow be defeated, because at the end, the fact of the matter is that the program has to run on computer or on your computer. So if you're using, for example, Photoshop or some program which is trying to not be reversible, it is running on your processor. So somehow your computer understands what it is doing. So since that means that the assembly or the code that it is running is on your computer. So however many like layers of protection there might be, it is still always reversible. For example, one of the recent examples of XZ bug, if maybe some of you saw it, where there was a vector in the XZ program which affected SSH. There was this very experienced people writing this vector, which was very hard to reverse. There was many layers of protection, but in the end, the world researchers and community was still able to understand exactly what it was doing, and that it was a vector that accepted arbitrary commands to run on the computer from a specific entity which had access to a private key. So even this vector, which was written by very sophisticated people, was successfully reversed by people, I guess, on Twitter or in the security field. Yeah, so I think my opinion is that there's no obfuscation that is undefeated for now. The best way to defend against this is to not have your code in a binary that user has access to. So a web server cannot be reversed, or something that is behind the server. But if you have the binary, then there's always a way to reverse it. Yeah, another question is about whether the programming language affects the time it takes to reverse engineer, and unfortunately it does, yeah, because all of these reversing tools were mainly written for C, and once you're met with binaries written in Rust or Go or Zig or any language which deviates from the patterns and patterns that you see in C, then the compilers get confused, and sometimes they don't support all of the features enough to well reverse the programs written in these different languages. So yes, I think it does affect the time, and it gets harder with the more complex languages. Yeah, another question is how to ensure the accuracy of information obtained through reverse engineering. I think there's no easy answer to this, because it's up to you. You have to understand the program, and there's always a chance of making a mistake. It's kind of like science, where you are experimenting, you are making a hypothesis of what you think the program is doing, and then you're reading the assembly to verify whether your hypothesis is true, whether what you expected the program to do is exactly it. And then when you verify, then of course you can be more sure that it is correct. But sometimes there's tricks, or there's cases where your expectation might be different from even if you read the assembly and think you're correct. Sometimes there's hidden tricks to lie to you during reversing. How to extract hidden or encrypted data from binaries? I guess you have to find the key of the encrypted data, otherwise it's impossible. And basically you have to, for those binaries where there's obfuscation techniques or packing techniques where the main code might be encrypted, you have to find the point at which the code gets decrypted. You have to find, you have to step through or figure out how the program is unpacked or extracted, and find the key that it is using for extracting, I guess. If it is not extracted, then sometimes it is impossible, because if the key is hidden, then it's impossible. But in the end, if some hidden code is running on your computer, that means it was unpacked at some point, so you should be able to find it. There's a few more questions. I'll go through all of them and we can finish them. The effective techniques for large binaries. For large binaries, I guess we talked about this. It's to know what you're looking for, use the strings or any information that you can easily obtain to quickly move through the binary to find the location or the relevant code that you're looking for, or that you're understanding or trying to understand, and only focus on that. Don't focus on reversing the whole binary. It's impossible sometimes. You have to use tricks like this of library importing or strings that exist in binary and its references to find what you're looking for, what questions that you want answered, and then you have to go through from there. You have to start from there. Yeah, I guess next question is also similar, so I'll skip that. And yeah, unfortunately, I'm not super sure about like industry side or like what skills are exactly required in binary reversing. But as a hobbyist or someone who does reversing for CTFs or for hobby, the skills is that, for example, if you're reversing C or Rust binary, you have to understand the language well. You have to, in general, you have to imagine how this program would be written. You have to make guesses on how it would be written, and then you can see if that is exactly how it is written. You can check if the assembly matches your expectation, and if not, you have to adjust your expectations. So in general, when I start to approach or reverse something, which, for example, I know what it does on the user side, or what it prints, or what it shows, then I can imagine like how I would write this and try to have that expectation when reversing, and which will help me guide through my reversing. And in the process as well, you have to adjust your expectations or modify or like adjust your expectations based on the code that you see. Yeah. The last question is about extensions or tools that help reversing, and I mentioned, yes, I mentioned 2 extensions for ByNinja in Rust. There's more tools. I remember specifically for Go, there's a Go strings extension. In Ghidra as well, I think. So the exact problem of like no null terminated strings, where the Ghidra is not able to figure out where a string starts and end. There's a similar problem exists in Go. So I think there was some extension which used to solve this. I'm not sure exactly which one, but I'm sure you will be able to find it when Googling. And in the resources, I'll also try to find any other extensions that are useful and link those as well. I'm less familiar with other languages because like my work or my experience only led me to like Rust or C or C++ reversing, since those are most common in CDFs. And the less popular the languages, the harder it is to reverse. So, for example, new languages like Zig or something, since they are very rare, there's no tools for those that exist. And I think it's also a fun project for anyone interested in improving reverse engineering to improve this ecosystem. So like write an extension that solves a specific problem of reversing some specific language. Those are usually not very hard if you spend some time on it, and it helps a lot of people when working on reversing those specific languages. Or so I think those are fun projects if you guys want to improve or improve your skill or do them for yourself. Yeah.
All right. Thank you very much, Alex, for your in-depth presentation here. We didn't really curate the questions, so some of them were on the same topic, but I think I can speak on behalf of all that we are quite impressed with how you deal with complexity, and looks like a lot of the students are wondering about that. So I hope that you are an example that they can follow and work hard and just dedicate a lot of hours and get to deal with such complexity that reverse engineering challenges everybody with. So I'm taking that there are no questions. If there's anybody in the other room, we're split in multiple rooms, please just raise your hand. If not, thank you very much for allocating time to meet us or to inspire us, and hope to see you again. We'll keep contact with Khokhiash, and maybe we can even share a beer at one time.
Yes. Thank you very much for inviting.
A lot of people would be happier to share that beer than reverse engineering. Yeah,
yes.
pretty sure. Let's focus.
Me too as well. Yeah. Thank you very much for inviting me. I'll also collect all the resources that I mentioned in, I guess, a document, and link it to Khokhiash so he can share it with you. And yeah, thanks for inviting, and yeah, hope we have a beer at some point in future with all of you. Okay.
Thank you. Have a lovely day.
Thank you. Bye, guys.